Hello, curious minds. Have you ever looked up at the stars and wondered, how did our entire galaxy come to be? Imagine this. Billions of years ago, the Milky Way wasn't the grand spiral we see today. It was a chaotic swarm of countless smaller galaxies, colliding and merging in the emptiness of space. So how did this cosmic chaos give birth to the beautiful galaxy we call home? Let's find out. To understand how the Milky Way began, we need to travel back almost 13.8 billion years to the dawn of the universe. Right after the Big Bang, the universe was a hot, dense mix of particles, protons, neutrons, and electrons, swirling through a rapidly expanding space. But within this chaos, tiny fluctuations, almost imperceptible ripples in the fabric of space-time, held the seeds of what was to come. These ripples were the first hints of structure in the cosmos, creating regions of slightly higher density, a cosmic patchwork of density variations. And in these denser regions, gravity took hold, pulling these atoms together into massive clouds of gas. Over eons, these denser regions pulled in more and more matter from their surroundings, hydrogen and helium, the lightest elements forged in the Big Bang, coalescing into vast clouds. These clouds of primordial gas became the nurseries of the very first stars, known as Population 3 stars, where the first lights of the universe would flicker into existence. The intense radiation from these early stars ionized the surrounding gas, stripping electrons from atoms, and creating a complex interplay of energy and matter. These ancient giants burned hot and bright but were short-lived, exploding as supernovae and enriching the cosmos with heavier elements. Surrounding these stars were invisible clumps of dark matter, cosmic skeletons that shaped how matter gathered. Inside these dense pockets, gravity pulled stars and gas together, forming small, primitive galaxies known as protogalaxies. These protogalaxies were chaotic and irregular, flickering with bursts of new star formation. They were the first building blocks of the Milky Way. As the early universe continued to evolve, these tiny protogalaxies didn't remain isolated for long. Gravity, the fundamental force driving cosmic evolution, pulled these scattered fragments toward one another. Collisions and mergers became inevitable. When protogalaxies collided, their gas clouds compressed and ignited bursts of new star formation, lighting up the darkness with brilliant clusters of young stars. Imagine two vast clouds of gas and stars, each containing billions of times the mass of our sun, hurtling towards each other at unimaginable speeds. But it wasn't just stars that were merging. Dark matter halos also collided and combined, weaving an invisible framework that shaped the growing mass. Over billions of years, countless mergers gradually built up the Milky Way's ancient core. These violent interactions often disrupted stellar orbits, scattering stars into a spherical halo around the forming galaxy, or flinging them out into intergalactic space, their paths forever altered by the encounter. Giant shockwaves would ripple through the merging galaxies, triggering bursts of star formation as gas clouds collided and ignited. But this wasn't destruction, it was creation on a grand scale. With each merger, the protogalaxies grew larger, more massive, their gravitational pull becoming ever stronger. And amid the chaos, a central bulge began to take shape, a dense, star-packed region that marked the heart of the young Milky Way. This bulge became the gravitational anchor around which the galaxy would continue to grow. As the Milky Way's core took form, leftover gas settled into a rotating disk, gradually giving rise to the spiral structure we recognize today. New generations of stars formed within this disk, while older stars remained scattered throughout the halo. Through relentless collisions and the gradual pull of gravity, the Milky Way transformed from a chaotic cluster of protogalaxies into a sprawling galactic system, a dynamic process that continues to this day. With the Milky Way's ancient core firmly in place, the next phase of its evolution began, the formation of its iconic spiral disk. After countless mergers and chaotic interactions, vast amounts of gas still lingered around the galactic center, slowly settling under the pull of gravity. Gravity didn't just pull the gas inward, it also set it spinning. Conservation of angular momentum caused this rotating gas to flatten into a disc-like structure, much like a spinning pizza dough stretching out into a thin, wide shape. Within this disk, regions of higher density began to collapse, forming clusters of new stars. Unlike the older, randomly oriented halo stars, these younger stars followed more orderly circular orbits, tracing the shape of the emerging disk. Over time, the combined rotation and gravitational pull sculpted the gas into beautiful, sweeping spiral arms. These arms weren't rigid structures but rather regions of increased density, where gas and stars moved through, compressing and igniting bursts of star formation. This continuous birth of stars gave the Milky Way its characteristic spiral pattern, a dynamic and ever-changing tapestry of bright young stars and glowing nebulae. The disk grew steadily, fed by remaining gas and smaller satellite galaxies drawn in by gravity. Over billions of years, the Milky Way's disk took shape, vast, rotating, and full of life, forming the iconic spiral structure that still graces our night sky today. Now let's take a closer look at the Milky Way itself, this vast city of stars. It's a majestic structure that has fascinated astronomers and stargazers for centuries. Our galaxy is home to a staggering diversity of stars, from dim red dwarfs to brilliant blue giants, each with its own story to tell. These stars vary not only in color and brightness, but also in size, temperature, and lifespan. These stars are not scattered randomly throughout the galaxy, but rather are grouped together in distinct populations that reflect their age and composition. This organization helps astronomers understand the history and evolution of our galaxy. The oldest stars in the Milky Way, formed in the early universe, are found in the galactic halo. This halo is like a time capsule, preserving the conditions of the early universe. These halo stars are like ancient relics, holding clues to the Milky Way's earliest days. By studying them, scientists can piece together the story of how our galaxy came to be. They are generally low in heavy elements as they formed before many generations of stars had a chance to seed the interstellar medium with the products of their nuclear fusion. This makes them invaluable for understanding the chemical evolution of the galaxy. In contrast, the stars in the Milky Way's disk, including our own sun, are relatively young and rich in heavy elements. These elements are the building blocks for planets and life, making the disk a fertile ground for new star systems. These stars formed from gas and dust that had been enriched by previous generations of stars, creating the conditions for the formation of planets and, ultimately, life itself. This cycle of star birth and death is a fundamental process in the galaxy. Within the galactic disk we find a variety of structures, each with its own unique characteristics. These structures include spiral arms, bars and rings, all contributing to the dynamic nature of the galaxy. The galactic bulge, a central region of high stellar density, is thought to harbor a supermassive black hole at its core, a monster that devours anything that ventures too close. This black hole plays a crucial role in the dynamics of the galaxy. The spiral arms, as we've seen, are regions of intense star formation, where giant molecular clouds collapse under their own gravity, giving birth to clusters of bright, young stars. And scattered throughout the disk, we find globular clusters, ancient groupings of stars that orbit the galactic center like swarms of bees. These clusters are among the oldest objects in the galaxy, offering a glimpse into its distant past. Although the Milky Way has existed for over 13 billion years, its story is far from over. Our understanding of the galaxy continues to evolve as new discoveries shed light on its complex nature and ongoing transformation. Thanks to advanced telescopes and space observatories, astronomers are piecing together a more detailed picture of our galaxy. One of the most groundbreaking projects is the Gaia mission, launched by the European Space Agency. Gaia is mapping the positions and motions of over 2 billion stars, giving us an unprecedented 3D view of the Milky Way. One surprising discovery is that the Milky Way's disk is not a flat, static plane. It actually ripples and wobbles, likely due to past collisions with smaller satellite galaxies like the Sagittarius dwarf galaxy. These gravitational interactions send shock waves through the disk, causing oscillations that can last for billions of years. But perhaps the most dramatic change lies in the Milky Way's future. Our galaxy is on a slow but inevitable collision course with our closest large neighbor, the Andromeda galaxy. Though recent studies suggest there's a 50% chance it might be a close miss rather than a direct collision. If they do collide, it won't happen for another 4 to 5 billion years. When it does, the two galaxies will merge to form a giant galaxy, often called Milkomeda. This dance will completely reshape both galaxies. Stars will be scattered into new orbits, and bursts of star formation will ignite as gas clouds collide. Despite the chaos, individual stars are unlikely to collide due to the huge distances between them. Even without major collisions, the Milky Way itself is constantly evolving. Star formation continues in the spiral arms, while old stars end their lives in spectacular supernovae, enriching the interstellar medium with heavier elements. Yet many mysteries remain. How much dark matter really holds the galaxy together? What role do supermassive black holes play in galactic evolution? And how will future generations witness the transformation of the Milky Way? With each new discovery, we realize that the story of our galaxy is far richer and more complex than we ever imagined. The Milky Way continues to evolve, and so does our understanding of it, proving that the journey of exploration is just as endless as the galaxy itself. And there you have it. The Milky Way story is far from over, and recent studies suggest there's a 50% chance that one day it will collide with Andromeda to form an entirely new galaxy. What do you think that future galaxy might look like? Let us know your wildest theories in the comments. And if you enjoyed this journey through cosmic history, don't forget to like, subscribe, and hit the bell for more mind-bending space stories. Thanks for watching. Until next time, keep looking up.